Whoa, I'm sorry about that, guys. I did not realize that my subscription to the service I use to record lectures, for some reason had expired, so it only let me do 15 minutes. Oh, 15 minutes! That's it. Okay. Anyway, so this is my f of x, y, z. So what I want to do is I want to find its partial derivatives to determine my gradient, right? So my gradient then of f in this case, if I take the derivative of this with respect to x, that z goes away, and then I just get the negative of f sub x, whatever that's going to be. Same thing with y, we get the negative of f sub y, right? The z would go away, and the derivative of this guy with respect to y would just, I don't know what it is, so I just call it f sub y. And then the derivative of z with respect to z is 1, and this derivative all goes to 0. So what would the equation of my tangent plane be then? It'd be f sub x evaluated at a, b, right, depending on where we're at, times x minus a, right, minus f sub y evaluated at a, b. Oh, I don't have enough room. Y minus b. And then plus 1 times z minus c, but well, how would I find c? Remember, I'm defined explicitly, so z would just be f evaluated at ab. And now what we're going to do is we're going to basically solve for z, and let's write this down as a definition. So I'm going to, sorry, it's senior day today, as we were chatting about this morning, so it's loud out there. So let's let f be differentiable at ab, blah, blah, blah. So the equation of a tangent plane 2z equals f of xy at some point, I'm sure you guys can hear that, ab f of ab is given by, all right, so if I solve for this z, basically I'm going to take these two and move them over here, and then I'm going to take this and move it over here. So it's given by z equals f sub x of ab times x minus a plus f sub y of ab times y minus b. And then notice here I'm just going to add over f of ab. And that's the only difference. So it's still pretty much the same. We just have that f of ab, and that's all. So let's do an example. And I got to clear that guy out. Okay, so example. Right, find the equation of the plane, tangent plane, that's pretty important, to this surface, z equals x squared e to the x minus y at my point 2, 2, 4. Okay. All right, so here's what we need. We need f sub x. So f sub x in this case, I would just have, I need to do the product rule, right? 2x e to the x minus y plus x squared e to the x minus y. That's the derivative of e to the x minus y. And then what's the derivative of x minus y with respect to x? It's just 1. So what would f sub x of 2, 2 be, right? Because I don't really care about the 4. Because it's just in terms of x and y. Well, here I would get 4. This would be e to the 0. Oh, isn't that fancy? Which is 1. Here I get 2 squared, which is 4 times 1. So we get 8. Then f sub y. Okay, I don't have to do the product rule here because x squared is considered a constant. So I just leave x squared. We rewrite e to the x minus y. And then the derivative of x minus y, right, with respect to y is negative 1. So f sub y of 2, 2. Again, I'm going to get 4 times 1 times negative 1, which is negative 4. All right, so here we go. So what is the equation of my tangent plane then? It kind of makes sense that it would be an explicit tangent plane because that's what we were left with. So I get 8 times x minus 2 minus 4 times y minus 2, and then remember it was plus f of ab, which is just that 4. There you go. And then if we simplify it, we would get what? 8x minus 4y, and then what? Negative 16 plus 8 is a negative 8 plus 4 is a negative 4. I don't know. I guess I do know, but I'm not sure if that's exactly right, but good enough. Cool. All right. Last thing. Well, two last things, a differential and a linear approximation, and then we're going to call it good. Okay, so really quick. So recall in R2, a linear approximation, right, was basically just, a linear approximation was basically just the equation of our tangent line. So it's basically the tangent line of my function at some point A, right? This is the tangent line. This is the tangent line because it's a line that goes through the point A, f of A, with slope of my derivative. So what this is we say that my function can actually be approximated by this line as long as we're pretty close to A. And we kind of talked about this already. We talked about the differential, which is a little bit different. It's the change in the, I should have been a little more careful when I was saying that. But anyway, a linear approximation, because the whole idea here is if I have a curve and I look at its tangent line, if we zoomed in on that piece right there, this curve right here would look more and more like a line. Well, that is also true for surfaces and planes. So I'm just going to restate basically what we've already done. In R2, our linear approximation was just the equation of the tangent line. Same thing, the linear, I'm getting really lazy. The linear approximation in R3 is just going to be the equation of the tangent plane. I know that's weird to call it linear when it's a plane, but remember a plane is just made up of a bunch of lines, right? So the linear approximation to some function z equals f of xy at a point. Now, I didn't put the f as differentiable, but you know it is just given by the tangent plane. Okay, so nothing special. Well, oh, it's special. Linear approximation, you're special. But I guess what I meant to say, to not hurt linear approximation's feelings, but has feelings, is that it's nothing new. It's just saying that if I zoomed in on a three-dimensional surface and I kept zooming and zooming and zooming, the closer I got to some point A, B, the more and more it would look like a plane, right? If I got in close enough. Okay, so let's do an example. I'm just going to do the one in your book so we can look at an interactive figure. Let's let f of xy equal 5 over x squared plus y squared. So part A, find its linear approximation at -1, 2, 1. Okay, and I'm just going to stay over here. Let me just erase some of this. The definition, remember, is just the plane itself. All right, so what do I need? I know I need f sub x, right? So f sub x in this case, so let's think of this as 5. I don't want to do quotient rule. All this to the -1. So it's going to be -5 x squared plus y squared to the -2 times 2x. So that's what, -10x all over x squared plus y squared squared. So f sub x at, what point are we at? -1, 2. Okay, if I put in -1, that gives me a +10. 1 plus 4 is 5. 5 squared is 25. Divide by 5, we get 2/5. Likewise, f sub y, I'll let you verify this. It's basically the same thing. It's just going to be -10y all over x squared plus y squared squared. So this implies then that f sub y of -1, 2 is just going to equal, what, -20. The bottom's going to be the same, over 25. So that's a -4, not 5. -4/5. So again, that's the gradient, right? Remember what that is. That's the tangent, that is the vector that is perpendicular to every single tangent line, okay? All right, so I have that, and so now let's just plug this in here. So I would have my linear approximation then, okay, would be 2/5 times x minus a -1, so x plus 1, minus 4/5 times y minus 2. And then remember, it's plus, right, this f of ab, so that would be 1. So that's plus 1. This is my linear approximation, meaning if I zoom in really close, the behavior of the graph around that point, -1, 2, 1, will mimic the behavior of this function right here. Okay, and then we had one more part to this. I should have thought about how I plan this out a little bit more. But B, let's estimate, use this to estimate the value of f at the point -1.05, 2.1. So again, we're really close to our original point, right? -1, 2. So if I take L of -1.05, 2.1, and I'm gonna grab this, since this example's in the book, I'm just gonna go, ooh, I just turned right to the page. There are things falling off my desk. Okay, not right to the page, but pretty darn close. Oh, no, I'm in 12:6. Isn't this great? You're listening to me flip through my books. Okay, so this is example 3 on page 932 if you want to know. But if we plug that in, what did I mess up here? Yeah, okay. Yeah. I just leave it like this. They simplified it a little bit. But if we plug that in, what we get is 0.90, where the actual value of the function at this point is 0.907, so pretty close. Now, why would we want to do this? I mean, this is silly in a situation like this, but if we had to evaluate something like this, that might take a while. Let's say I was doing lots and lots and lots of evaluations, and I want to know lots of times what happens when I change from a certain point. It could take a lot of time on like a computer to program that, for the computer to evaluate a fraction and squareds at the same time. I know it doesn't seem like much, but if we were doing it a bunch, whereas something like this that's linear would be a little bit easier. All right, guys, last thing. Oh my gosh. See, look, it was 15 minutes in the last video. I'm only at 12 minutes in this video, so I'm not even going to go for a full hour. Last thing, definition. And I'm just going to put this down, and then we'll talk about how it looks a lot like our differential in R2. If you would like to look at kind of the work for this and the argument for why this is true, it's on page 932, the last half and the beginning of 933. But we're just defining the differential. So, oh, blah, 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 let's let f be differentiable. Yeah, we know that, right? So the change in z, some function z, which is f of x, y, right? As AB changes to, okay, so here's what the differential tells us, right? As AB changes to, I'm just going to go a little bit away from A. Remember, A is x, so I'm going to call that dx. And I'm going to go just a small distance from B, so that's dy. It's denoted delta z. So not upside down triangle, delta z. This guy is approximated by the differential. And what we call that is dz. And here's what we got. So the change in z. So again, what is this showing? If I have z as some function, okay, and I know its value at AB, what I want to know is what is the change in my function values if I just move a little bit away from A, and if I just move a little bit away from B, okay? And so this guy is approximately, this is what we call the differential. You may remember some of this from Calc 1, or maybe you don't. And what this is going to be is just f sub x. We kind of talked about the differential when we did that example with the volume. F sub y of AB dy. And remember, the differential in R2 was dy equals f primed of x dx. So notice we kind of have those two parts, right, with our partial derivatives. Again, you're welcome to read through that because I'm really trying not to make this too long. So the example I do, let's go back to my function z equals 5 over x squared plus y squared. Oh my gosh. Do you hear that cart? This happened in differential equations. That cart must know when I am recording a lecture in my office, or that person. And it's and it's just it's like, all right, I know Sarah's recording a lecture. Let's find a cart and let's push it up and down the hallway. Okay, so approximate the change in z when the point -1, 2 changes to, right? Now it needs to be, notice these are small changes. I'm sorry. I just think that's funny. I just think it's funny that that cart is going by. So fairly small changes, right? 7 100ths, 6 100ths here. And so how we find that is we just evaluate this guy right here. Now, notice that what we mean by that AB is at my initial point. So to estimate this, I want f sub x of my initial point, -1, 2, and then times, I'm going to take the difference between these two. So where I ended, right, minus where I started. That's my change in x. That's dx, okay? Plus f sub y of -1, 2 times where I ended minus where I started. Okay, those are going to be my changes. So if you go through and look at this, remember this guy right here, I think was 2/5, right? Times what? 0.7 or 7/10 plus, and I think this one was like a -4/5. Was that right, you guys? We already did this, right? Yeah, 2/5. Whoops. Okay, 2/5 and 4/5. Okay. Okay, and then times, what do we have here? A -0.06. Okay, I see it. I see it. I see it. Are you yelling at the screen? 0.07. So what we have here is 0.076. So again, what does that mean? This is the approximate change in my function value if I make a small change in my x and my y. And the actual change, they show you in the book, the actual change, if we actually plugged in those numbers into the function itself and took the difference, was 0.08, so it was a pretty small change. Approximation has about a 5% error, not even a 5% error. All right, you guys, that's it. 18 minutes, 15 minutes for the last one, like 33 minutes. Did I do that? 32 minutes, 33 minutes? It's actually not too bad. I have your homework. I will put that in the email when I send you a link to this lecture. You guys rock. Have a wonderful weekend. I will miss you this weekend, and I'll see you on Monday. Email me if you have any questions.